All right, let's see. Good evening, folks. My name is Rochi, David Roach. I'm part of Expat Audio, and I'm here this evening to try out this whole web streaming stuff and to talk a little bit about the Expat Audio TinyVU board. Now then, let me make sure you guys can hear me okay. I'll just kill that. Okay, let's go full screen for just a moment. So the TinyVU board is something that I've been working on probably on and off for about a year now, if not more than that. And we posted a couple of videos along the way, and really kind of got disheartened for a while there at the progress we were making and so on. So what I've done is decided to kick my own ass a little bit, share what we're working on so far, and get feedback from the community, from you guys, on what we want to do moving forward. And so without any further introduction, please excuse the clicky mechanical keyboard. But the main reason I developed this really is because I'm tired of the LM391X. For those of you that don't know, the LM391X is a laser-trimmed analog product that's looking pretty long in the tooth right now. So it's a bunch of comparators that will drive LEDs. And you have to do a big external circuit in front of it to condition your audio, to do the rectification and so on, so that it can drive the device. So as I said, it's looking a little bit long in the tooth now. The steps are actually fixed steps, and there's an LM3914, LM3915, and an LM3916 that each have different fixed steps to be able to give you either 3 dB linear, not linear, but 3 dB steps for each of the LEDs, or some of them a bunch of steps around the 0 dB point and then big steps below that and so on. And I thought to myself, well, in a software configuration, I could probably change that on the fly and change the product for how I'm using it at the time. The other thing that's a pain with this as well is that the peak hold and the regular running VU meter are actually two separate front ends that you then have to switch between really quickly, and there's a play on the persistence of vision in the part to do that. So what I wanted to do on the TinyVU really was to enable the integrator, you guys, to really just be able to either use a jumper and a pin to say I do want peak hold or I don't want peak hold. And so the design itself is actually done. We had to do one revision because of an issue with grounding, but we can come back to that another time. But essentially, the board design is done. You can see there the board working. I'm not sure if you guys can see the mouse pointer here, but what you essentially have is these two lines are actually a serial port connection, so you can use your computer to set this up to set the levels and so on. And then over here, this is power and the audio signal coming in. And then this trim pot then is used to configure in real time, what that full scale signal is. And so we put in a range of about 10 dB either way, so that you can trim it one way or the other, just in case you're plugging it into an iPhone, or you're plugging it into a Pro sound card and you need a lot more voltage out of it. So the board design is done, but I think it's the software is killing us at the moment, frankly, and I can talk a little bit more about that. And I can also address any questions you might have. I've got my trusty laptop on the side here that's running YouTube chat as well, so you can ask any questions there, and I'll address them as they come in. Otherwise, this might be a short show just to show like the start of the project, and we'll take it from there. So from a hardware perspective, this is a little different from what an LM391X would be. With an LM391X solution, you'd still have, if you're doing the design properly, some kind of input buffer, and you'd have a precision rectifier. And what a precision rectifier does is it takes all the negative signals and actually just makes them, a double positive, if you will, a full wave rectifier. So essentially, if a sine wave is going positive and then negative, this will make it into a double positive. And so what that means that you can then use that to drive a meter like an old school analog meter really well, or you could drive an LM391X, or in this case, I'm using it to actually drive the analog to digital converter of a microcontroller. Now, a microcontroller is a lot like, you know, the processor in your PC, right? It executes commands, but typically in a microcontroller, it's much slower, much lower power, and typically you get many more mixed signal analog style blocks in the part as well. So for instance, you know, you would get ADCs in a part. You could get a clock generator for doing PWM. That's very similar to the analog output on an Arduino, if you're familiar with that. In this case, we're doing in this case, this is an MSP430 microcontroller from TI. I work at TI during the day. What we're doing in there is we're actually running a software, that's the SW, low pass filter and comparison. So what it's doing is it's doing a little bit of filtering inside just so that the response isn't so fast your eyes can't see it. And then on top of that, then it's doing a software comparator. So it's saying, hey, if the value coming in from my my ADC is, you know, half of the voltage of the maximum voltage I can take, then I need to light up these LEDs, and it'll light up sort of, you know, most of them except for maybe the top 3, for instance. And so the idea behind that then is that those levels, that comparison can be changed by the user using this serial port. So the idea is, you know, once you receive a board from Expat Audio, you will, if you want to change the levels and the trigger settings and so on, you go on to Amazon, or you go on to Taobao or AliExpress, and you could buy a very simple dongle for your PC that's a USB to serial converter. And then that taps into this board, and you start the program up, and you can say, hey, I want to you know, change these levels so that they're all up near maximum volume, so I can, you know, fine tune and push my levels as close to full scale as possible, for instance. And then that then drives an LED array, which is a bunch of little lights all running together. And I also have a configuration switch here, which I'll be setting up so that you can use a physical switch on the front of your product to put peak hold or not on there as well. All right. So doing the design of this circuit, I was looking for a very good precision rectifier. Now, some of you may be familiar with a full wave rectifier that you would use in a power supply. Yeah, typically you'll have a transformer and then a four-way diode bridge, right? But the problem with that is that you actually lose some voltage drop going through those diodes. Now in a power supply, who cares? You lose 0.7 volts. You've already got 15 volts or something going in. But when you want to measure the exact signal, and the signal you have coming in is in the low millivolts range, well, then it becomes a problem. So the way we solve that is actually using an op amp and some diodes there, and you bias things around it. And I went looking around online, and what I actually found was an old Burr Brown book that had this really clever schematic in there, so that you could do it with just 2 op amps. Everyone else I'd looked at were looking at, you know, 3 op amps, 4 op amps, and lots of passive components, resistors, caps, diodes around it. And so that was one of the things I'll show in a moment. And then the original design we did, this is the second board. The original design, I used a regular op amp, you know, the one we use in audio all the time, NE5532 or something like a TLO72. But they needed plus and minus positive supplies, and that's that's typically a very typically in audio. But you know, for this board, that op amp would be the only device using a negative supply, and what a pain to generate that. So what I did was I found a device again from TI, talking to some of my colleagues, called the DRV632. And the great thing about this DRV632, it's a you know, pretty good op amp. Typically, it's used on the output of a set-top box for your television, where you want to drive a plus or minus signal, wave out into your TV or into your stereo or something like that. And what the DRV632 does is it's actually an op amp that creates its own negative supply. So it's enough for it to run itself. And it does this using a charge pump. Some people have concerns about charge pumps, but given that this DRV632 has a history in audio line-out applications, I really wasn't that concerned. So let's have a look. So yeah, this was the old book I found. This one was by Burr Brown. Again, Burr Brown was acquired by TI back in 2000 or so, and this schematic here kind of screamed at me in the face. It's wonderful, right? Because it's two op amps that I already have, a pair of diodes, which you can actually buy a pair of diodes in one small surface mount package, and then finally those two op amps. And depending on how you set up the values of these resistors, in this case they're all the same value of resistor, which is again great for us because when you're manufacturing surface mount products, you really want to use the same value of resistor as much as possible throughout the circuit. So being able to use the same circuit again and again and again and again, you're just telling a machine, pick up the same part as you did last time and drop it down here. Pick up the same part again, drop it down here, and so on. So let's jump out of this PowerPoint really quickly, and let's jump to the schematic view. And you can see here, hopefully this is coming through well enough for you guys. This is the actual circuit we used at the front end. And I'm going to zoom in a little bit more just for those of you watching on terrible cell phone screens and stuff. So on the input we have a 2.2 microfarad capacitor along with a 10k ohm input. Now this actually creates a high-pass filter of sorts, but it's not too much to worry about as the values for the resistances are high enough. And again, this is a visual aid. It's not something I'm not going to be listening to the output of this circuit. It's purely visual. So that goes into an additional potentiometer here, which gives us the ability to scale the input up and down. So I can add gain, remove gain, and so on, all in this circuit. Then I have a bunch of op amps around it. A bunch of resistors. This is the DRV632. And then this is the BAV199 dual diode. And it's basically a 3-pin, it looks like a 3-pin surface mount transistor, but it's actually 2 diodes. And I just drop it straight across here. Very, very, very easy to use. And then you can see my notes here. This little RC here is actually a hope in making response viewable. This was when I was convinced that the issues I was having was in the analog domain and not in the digital. I've done some debugging since then and found that actually I can actually bypass this with a short and leave this open. Now the DRV632 actually needs a few more devices, a few more things just to make it useful. And so what we have here, a few more connections, I should say. You have a charge pump here, so we use a 2.2 microfarad cap, and you'll see 2.2 microfarad caps all over this design because, again, once it's in the machine, once it's in a reel of parts on the pick and place machine, I just say use the device that's in reel space 5 and just pop it there and pop it there and pop it there and pop it there. So we've got 3.3 going in, ground on the other side, and it works beautifully, quite frankly. And then we also have a mute pin, so I just set that pulled high, and it works nice. This UVP is an under voltage protection that will mute the output if this power supply begins to fall. So not when it's down to 1 volt, but if it falls down to 2 volts, for instance, the DRV will mute. All right, let's walk through a little bit more of the schematic then, shall we? Because the schematic itself is quite simple after you've passed that analog stage. So this is the MSP430 microcontroller I'm using, and you can see here there's a power supply and ground. We bring in the rectified audio, rect audio here into pin 1.0, And then from this TXD and RXD are my serial port inputs. So these connect, back to the PC through a USB dongle. Then everything else here is what we call GPIO, that's general purpose IO, that goes over to the LED array. I'm actually going to show you a closer picture of this in a moment, so let's jump back to that real quick. Here we go. And so here's my mouse pointer. Okay, so here we have the microcontroller, and here's the front end DRV632. So the DRV632 and the circuitry around here feeds directly into this, and it feeds it a signal that is positive only. Okay, and at which point the ADC, the analog to digital converter that's inside the microcontroller, is sampling it, and running this conversion. And with that, then it compares it with a list of numbers just to make sure it's all running well. So let's talk about the serial commands. So as I said, with a cheap USB dongle, you can hack in and change the trigger points. And let's jump to a small video I did on that last year. Let's make sure that works. I'm going to press play and see if it works. So this is a little program on a PC called Hyperterm, and Hyperterm taps in over the serial port to the microcontroller. So this text you're seeing on the screen is actually coming back from the microcontroller into my computer and then going onto the screen. And so this whole menu like this is basically all coming back from the microcontroller. Very, very easy to use. And so you can see the peak hold value. I changed the peak hold value there so that it holds onto the peak a little bit longer before starting to fall again. All right, so I think I've brainwashed you enough with that one. Now to calculate the values for those, I actually created an Excel file. Let's see if I can zoom in here. So I would say, okay, if I want 2 dB steps to begin with, let's zoom in a little bit more. Here we go. Okay, so I can zoom in and say, okay, my top value is full scale. So let's say that's plus 18 dBu. I could set that to be the 0 dB value point of this converter. And then I say, well, if I'm 2 dB away from maximum value, I put in -2. I put in -4 for the next one, 6, 8, 12, 16. And then let's say I want bigger jumps so that I just know if there's any signal coming in. I put all those values in, it does the math, and then you type in these values to set that in the interface. So once you've got the serial connection made, you would type W91024, and that would set that last LED to require you to clip the input before it flashes. And the same goes for every one of the steps down. All right. And then finally, this is some of the kind of stuff. So some of the front-end debugging I had to do was to actually look at, for some reason, the peak hold was actually like staying 1 or 2 LEDs above the actual peak point that we were seeing in the audio. And so I was worried that I was getting some kind of spurious noise coming from that front end. Maybe it was some kind of tone, out at the switching frequency of the charge pump and so on. So one of the first things I did was actually put in, grab my scope, got a 1 kilohertz test tone, and put that into the device, and then started measuring not only the time-based response here, but also looking at the FFT. And the FFT is the fast Fourier transform. It actually gives us a method to look at the frequency spectrum of the incoming signal. And so, for instance, here, you see, this is the full rectified 1 kilohertz signal. That's looking great to me, quite frankly. And the difference in level here is not enough for me to be really worried about 1 LED or 2. Now, the scope is telling me that it's a 2 kilohertz tone. And the reason it's saying 2 kilohertz is because when you full wave rectify, you have a rising edge twice, right? So rather than rising and then falling, and then rising, you get rising. And so that told me, hey, my signal's looking pretty clean. I don't see any major high frequency noise. And so the next thing I did then was look up what my frequency content was. So by running my FFT. And each of these blocks is worth about 2 kilohertz. Sorry, 5 kilohertz. So 5, 10, 15, 20, 25, 30 kilohertz, 40 kilohertz. Now we're beyond the hearing range. And I was a little bit concerned about this, and I thought, oh goodness, shouldn't this just be like a 2 kilohertz tone? But a few minutes later, in a quick Google, FFT of rectified signal, and boom, it looks exactly like that. So at which point I became very, very convinced that there was something wrong in the low-pass filtering I was doing on the device. The low-pass filtering I was running in software, and so that's where I am now. That's what I'm going to be working on in the next 2 weeks, is trying to understand what I was doing wrong, because what I was actually trying to do was a averaging filter. Just a long averaging filter that looks at 32 samples one after the other. And what I realized was that because this ADC is running so quickly, and at top speed it's running at like 60 kilohertz, averaging 32 samples doesn't do enough for me. So I've got to really jump back into the circuit design and see what I can modify with that. Anyway, so that's the end of tonight's broadcast, if you will. I don't really have that much more to show in any way, shape, or form. I did want to show a cool purchase, if we're going to talk about electronics and stuff like that. I spent a little bit of time today with the guys at Cadsoft. So let's see if I can open this. Cadsoft USA. These are the guys that make the Eagle layout tool. And so let's have a quick look. They make Eagle, right? And so one of the things I was working on was, I'm currently running an Eagle 5. I want to jump to Eagle 7, and I contacted them, and I was even on the online chat with them just to see if I can get a good deal or whatever. And let me open up this pricing table here so you can see what I saw in horror. So to be able to handle the layout size we need to do, just for schematic and layout, it's $575, and I thought, oh, that's a little bit much, So one of the things I did, here we go, let's have a quick look here. So business standard, here we go, $575 for layout and schematic. And to be fair, when I did contact them on the chat, they did actually offer me a lower price. They offered me a little bit of a discount that was enough to save the sales tax or something, VAT in Europe. But that's not in the realm of an impulse buy. So what I did find, I was in Micro Center later in the afternoon. Micro Center is a store here in Dallas, in Texas, that does computers and hobby things. I found this guy. Now this guy, I'm not sure if you can see it very well. We'll wait until it refreshes on the screen. So this guy is it's a Raspberry Pi 2, but they also threw in a copy of Eagle Make Personal into it. And so Eagle Make Personal, technically I can't buy it, if I'm using it for business purposes, but because it's in the box, you know what? I should be able to use this just fine. So for $169, I get a full copy of this that can do 160 millimeter by 100 millimeter, which is more than most of my boards are. 99 schematic sheets, 6 signal layers. So I'm not doing 6-layer boards. Most of the time I do 2-layer boards and 4-layer when I'm feeling really brave and rich. So for $169, I've got a Raspberry Pi here, which I plan for a couple of projects moving forward, and a license for it. So that's really worth looking for. It's called the Eagle Make Personal with Raspberry Pi 2. And I truly wouldn't be surprised if now that we have Raspberry Pi 3, they'll be updating this to show that. But yeah, that's the new and cool thing. I'm looking forward to using that a little bit more, especially with some of the hierarchical design elements that you can do in the new Eagle 7, where you can make a block diagram essentially and be able to jump into each component and hopefully save that component and use it in other designs. So for instance, power supply designs, my rectifier circuit, all of these could be recycled and reused from design to design. So that's all we have to discuss today. please feel free to come on to www.expataudio.com. I'm occasionally on the chat system there. Otherwise, our Facebook group at facebook.com/expataudio is, there's things popping up on my screen all the time. You may have seen one just now with folks asking me questions about the products and so on. And then real quick, I just wanted to show, maybe I can do this. I'm going to have to take the webcam off for this. But there you can see it's actually monitoring the output from my laptop. So I'm streaming this show back to my laptop. And you can see right there the VU meter is running and responding to my voice, be it a little delayed. And so, yeah, let's get a little bit closer. So we still have a little bit of work to do just to make the peak hold reasonable. But once that's done, these boards will be available in arrays of 4. So you'll buy like 4 at a time from us. And the reason it's 4, and I'll cover this later, is that we actually build them on our pick and place machine, which is our surface mount machine, in boards of 4. Any bigger, and you run the risk of failures across the board if the parts become slightly misaligned. But 4 seems to be tight enough so that the machine can put the parts down in the right places and so on. And I'll do another video about that soon. But for now, I hope this video came through well. And if you have any questions, let us know on the Facebook group. Cheers, guys. Appreciate your time.